Welcome to Basics of Finite Element Analysis Part 2. Today is the second day of this week. Yesterday what we were covering was the details of numerical integration using Gaussian quadrature approach, and what we had developed yesterday was the relation for Gaussian integration. So, suppose we have to find the value of Kij, and then we have to basically transform the whole integral into zeta eta space, and once we are successful with that endeavor, then we use the Gaussian quadrature method to find the integral using this relationship. So, please note that here indices capital I and capital J correspond to the index associated with Gaussian quadrature point. So, for each Kij I have to add up several times based on the values of n and m, and that is how we calculate the value of Kij. If Kij, so this index Ki, the lower case index, each time it changes I compute a different value. Each time it changes I compute a different value. So, I compute K11, K12, K13, K14 and so on and so forth. But for each calculation of integral I have to do this addition over a different index capital I and capital J, and that is how we go around doing that. Let us look at some locations of some of these points. So, if I have a linear element so, if I have a linear element, then the maximum degree, if I use Gaussian quadrature, it will help in integrating it accurately will be, so polynomial degree. So, if I have to use a linear quadrature, then in this case there are two quadrature points in one particular dimension. So, order of integration is 2 times 2, okay, and the residue or the error, as I keep on shrinking the size of my element, the order of that residue, it goes down in this fashion, where h is a normalized length of a typical element. And what are those locations? So, this is my element. What is this element on which I am integrating? This is a master element, okay. So, I evaluate, see if I evaluate f at zeta I and neta j. So, I evaluate at these points, and what is the location of this point? This is 1 over square root of 3. So, the lower point is minus 1 over square root of 3 below the zeta axis, and the same thing is also true for these other 4 points. So, what do? I evaluate the value of f at these 4 points. I know the coordinates of these points, I have specified it in this picture. I evaluate this f because I know all this expression, I know everything in this expression. In this expression I know everything. So, I evaluate this entire complicated expression, not the integral, the integrand, the value of the integrand at these 4 points, and at each point I multiply it by this weight, Gaussian weight, and these Gaussian weights we have given to you in our earlier discussion on Gaussian integration. So, these are standard weights. So, I do this and I get my integral. If my expression is more complicated, say psi I is quadratic in nature, then del psi I will be linear, because del psi I over del zeta will be linear because I am differentiating it. And let us say that A is quadratic, A could be quadratic, cubic, linear, constant, whatever. So, if the overall integrand is more complex, then I use quadratic quadrature. So, this is linear quadrature, I use quadratic quadrature. Here I can handle up to 4th polynomial degrees. Okay. So, I can integrate polynomials up to 4th degree, and in this case the order of integration is 3 by 3, and here the residue, as I keep on reducing the size of the element, it shrinks faster than the linear system. So, it is O order of h to the power of 6. So, let us look at the quadrature points here. So, once again this is the master element, this is minus 1 1 or minus 1 minus 1 1 1, and I evaluate it at nine points. These are the 9 points, and the spacing between these 9 points is 3 by 5, square root of 3 by 5. The same spacing is also in the y direction. So, here capital M and capital N are 3, these terms, and if I have even more complicated or not more higher order polynomial, I can go up to cubic quadrature. Here I can handle up to 6th order polynomials. Here I have 4 by 4, that is 16 quadrature points, and the residue converges at h to the power of 8. It is extremely fast convergence, and let us look at okay. So, what are the locations of these points? This distance is 0.339 and this distance is 0.861. Same distance, so same things on the other side of the zeta and eta axis also. So, in this case I have to evaluate the function f at 16 points, multiply it with appropriate weights. These are not functions, these are numbers, appropriate weights, add them up and I will get the integral. So, in this way I can calculate any stiffness matrix or any element of this force vector using this Gaussian quadrature method. So, this completes our discussion on Gaussian quadrature. So, we will move on to the next topic and we will briefly discuss post processing. Post processing. So, we have learned how to formulate the problem, how to discretize the domain, break it up into individual elements. We have learned how to develop a weak form. From the weak form, if we introduce in the weak form approximation functions and weight functions, then we get finite element equations. So, we get equations for each element. We have also learned how to assemble these equations, and in that context last week we had discussed the this connectivity matrix, and we have learned how to assemble elements when different elements come together and share a particular side or a node. So, we learned all this and also how to apply boundary conditions and solve the problem. When we solve the problem, what is it that we get out of the problem? We get the values of primary variable, right. So, once we solve the assembled equations after applications of boundary conditions, we get values of primary variable. And at what locations do we get these values? At what locations do we get these values? At nodes. So, we get these values at nodes. So, the finite element equations, once we solve them, we get values of primary variables. We do not get values of secondary variables, forces or stresses or strains or heat transfer rates or flow and all that stuff. We get specific values of primary variables, and that too we get it at specific nodes. Now, suppose there are two elements, element 1, element 2, and these are the local nodes, and these are global node numbers. Okay. When we get the solution of primary variables, what will we get? We will get this entire vector. Right. We will get the solution for all the nodes. Some nodes we may also already know in the beginning because of boundary condition, but once we have done the whole finite element analysis, we will know this vector completely, right. And while we are doing that, so when we are solving this, we get this completely, and in the assembly process we ensured what? Continuity conditions. So, we ensured that u1 at node 3 was equal to u2 at node 4. Similarly, we actually equated, and this we equated through the connectivity matrix, right. We equated u1 at node 2 is equal to u2 at node 1, and this we called u2, no I am sorry, this we called u3, global node 3, this is u2 and this is u5. Now, suppose the first thing we may be interested in is we want to find out the location of u at the value of u at this midpoint or some point. Then what do we do? How do we find it out? So, we know that for element 1, so let us say the coordinates of this point are x1, y1. So, we know that for element 1 u for first element is what? Right. U for first element at any location in this element, is uj, which is the value at jth node times psi j evaluated at xy. When I add this up, I mean this is how we formulated the problem, right. So, if I have to find the value, suppose I have to find the value here at point P1, and let us say the coordinates of point P1 are x1, y1. Then how do we find out the value at point P? Suppose I am interested in finding the displacement or value u at P. All I have to do is in this relation plug x1, y1, right, and we already know uj's. How do we know uj's? Because this is known. Right. So, uj's are known, also psi j's are known. These are approximation functions, we have already developed those. I can do this either at the global level or the local level, does not matter, but I know uj's, I know psi j's. So, all I have to do is plug x1, y1 and I will get the value of u at point P1. So, this will give me point P1. Now, here is the question. Suppose there is another point P2. So, let us say point P2 is x2, y2 in global degrees of the global coordinate system, it is x2, y2. How do we find out the displacement at point P2? Should I use element 1 or should I use element 2, or I use both and then what do I do? See, if I use element 1, then what is the value? u1 at x2, y2. So, I have to put a subscript now, I have to be careful. So, at location x2, y2 which is point P2, j is equal to 1 to 4 uj for the first element, psi j for the first element x2, y2. So, I will get some value at point P2, right, because this point P2 is in element 2 as well as on element 1, right. I can also get it u2 x2, y2 is equal to j is equal to 1 to 4 uj for element 2, psi j for element 2, x2, y2. So, these are two different formulas. Which formula is correct? Or both are wrong? Or both are correct? Both are correct. So, why are both correct? Huh? See, we had ensured that u was continuous at point 5, u was continuous at point 2, and between 5 and 2 this is a linear element. How is it varying? If it is a linear element, how does it vary? It varies linearly. So, u at 5 maybe the displacement is this, u at 2 maybe the displacement is this. So, this is node 5, this is node 2, these are global nodes. How does the displacement vary? It varies like this. So, it does not matter if I am looking from side 1, it will still vary. in a linear way. If I am looking from element 2, it will still vary linearly, because and the value at this midpoint P2 will be same, because why? Why will it be same? Because these values are same. So, I can use either of these values to get P2. I can use either of these values to get P2. Next, we look at derivatives. So, consider element 1. So, this is element 1, this is element 2. Local nodes are 1, 2, 3, 4, 1, 2, 3, 4. Global nodes are 1, 2, 3, 4, 5, 6. Suppose I am interested in finding the derivative del u over del x, and I am interested in finding it at, let us say, point P1. So, how do I find the derivative del u over del x at point P1? What is the relation for u for element 1? U for element 1 equals what? Uj psi j xy, right. So, if I have to differentiate, I have to get del u over del x at point P1. What do? I just differentiate this term, uj del psi j over del x, and where do I evaluate it at? x1, y1. So, if the coordinates are x1, y1, I get this relation, and that will be my derivative. Now, suppose this is point P2 and point P2 is x2, y2. Now, I again have two options. I can compute from element 1 and I can compute from element 2. So, if I compute from element 1, then del u over del x at point P2 from element 1, and this is equal to, oh, there has to be a summation sign here. And if I am computing from element 2, so here I am using element 1, so the superscript is 1. And in the other case I am using data from element 2, so the superscript is 2. Which one is right? Derivative is, did we enforce continuity of derivative when we were doing assembly? Where did we enforce that? Where did we enforce the continuity of derivative? Did we ever enforce continuity of derivative? We never enforce the continuity of derivative, which means that if I calculate from element 1 the value of this derivative, that number will be same or different? It can be different. It can be different. So, these two values need not be same. See, when we do beam equation or some other equations, there we specify continuity of derivative also, but in this formulation we never specified continuity of derivative. If we specify continuity of derivative, that also becomes a variable. So, in beam equation, if you remember, go back to Euler-Bernoulli beam, each node has how many degrees of freedom? It has 2 degrees of freedom, right. Here it has only 1 degree of freedom. So, we only specified continuity of the primary variable, we did not specify continuity of the derivative. So, these relations need not be same. So, if you use element 1 to calculate the derivative, you will get one answer. If you use element 2, you will get the other answer, another answer. Which answer is correct? So, the answer is, this is a finite element solution. So, these differences and even higher order derivatives, what happens to them? They go down, they reduce as what? As we keep on reducing element size. Okay. So, these differences keep on reducing as we keep on reducing the size of the element. Okay. So, what we have to make sure is that we should feel comfortable that the movement or the change in derivatives as we cross the boundary of an element is sufficiently small. Only then we can say that the solution has converged if we are interested in finding out derivatives. Where are derivatives important? For instance, if I have to find strain, then what is it? It is related to del u over del x, del v over del y, del u over del y plus del v over del x, and so on and so forth. So, if I am finding interested in finding strains and I am interested in finding strain especially at the point which is at the boundary, then I have to make sure that the number is, the difference between side 1 and side 2 is sufficiently small. Where else? We know that stress is what? It depends on strain. If you multiply stress by elasticity constants, you get stress strains, you get strains stress. So, stress, if I am interested in, again we have to keep on reducing the mesh size to sufficiently small level so that it is converged. So, this is very important to understand. Okay. This is very important to understand that derivatives are not continuous in a lot of FEA solutions across an element boundary, even though the displacement or primary variable may be continuous, even though primary variable may be continuous. So, I think this closes the discussion for numerical integration and also today's lecture. We will now move on to the next lecture, which is tomorrow, and till then have a great day. Bye.